Okay, so Chapter 2 is concerned with different systems of units that we're going to use in science, or chemistry in particular, and we're going to do this really important topic of dimensional analysis. And I assure you that the sooner you get used to attacking problems using a dimensional analysis strategy, the happier you will be. So we're going to begin with some basics of the metric system of units. So every measurement, as we mentioned before in Chapter 2, has at least, three parts. It has a number that's sometimes called the magnitude. It tells you the size of what is being measured. It has some measure of the uncertainty, and if that is not mentioned explicitly using plus or minus notation, that is plus or minus 1 in the last significant figure. And then this is important for this particular chapter. It has units, and the units tell you what is being measured. So that's the importance of the units. So for example, if we see units of gallons, we know that volume is being measured. If we see units of miles, we know that length is being measured. So when I look on this drug fact sheet, it's for an antihistamine, I can see here that the active ingredients, there's 2 milligrams of it. Milligrams is a unit of mass. So in science and engineering, we use the International System of Units, which is the modern version, the most up-to-date version of the metric system. We call this the SI system of units because it was developed in France, and in French it's Le Système International. So the metric system is preferred over traditional or English units because the relationship between different units are always powers of 10. So if I look at the relationship between the units of length of centimeters and meters, you can see that the difference there is a power of 10. Similarly, when I look at units of volume, the relationship between milliliters and liters is also a power of 10. In English units, the conversion factors between different systems of units are kind of random. And for example, relating feet and inches, it's 12, but relating gallons and quarts, it's 4. So this makes things hard to, to memorize what the conversion factors are. We might be able to easily remember how many feet there are in a mile, but when we come to sort of thinking like something like how many inches are there in a mile, it suddenly starts getting more complicated. Or if I want to give an example in volume, how many tablespoons there are in a gallon, most people don't know. So the SI system has 7 what we call base units, and the ones that we're going to be most concerned with are really the first 5 of these guys. We won't be dealing with electric current and luminous intensity very much at all, although we deal a little bit with this guy in Chemistry 163. So the base unit for length is the meter, and it has a unit abbreviation of a lowercase m. The base unit for mass in the metric system is the unit the kilogram, which has abbreviation a lowercase k followed by a lowercase g. For time, it's the familiar second, which is indicated by a lowercase s. For temperature, it's the Kelvin, which is indicated with an uppercase K because it's named after a man, Lord Kelvin. The amount of a substance is given the unit name the mole, and that has unit abbreviation all lowercase MOL, and then ampere, uppercase A, and candela, lowercase c and d. Now, it's probably obvious to you that there are more than 7 things that we can measure, and what we do to get units for those other quantities is we combine these 7. So for example, the SI unit of area would be the SI unit of length multiplied by the SI unit of length, which gives us meters squared. The SI unit of speed in terms of the base units would be length divided by time, so that would be meters divided by seconds. So in this way we can build up other units for things that are not amongst these 7 here. The metric system has this really cool system where we have these what we call metric system prefixes, these are letters that act as though we are, that indicate that we're multiplying by a particular power of 10. There are 6 that I would like you to memorize: mega, kilo, deci, centi, milli, and micro. Each of these has a letter, and the case is important, that is equivalent to writing multiplication by a particular power of 10. So mega has the symbol uppercase M, kilo has the symbol lowercase k, deci has the symbol lowercase d, centi has the symbol lowercase c, milli a lowercase m, and micro has the Greek letter mu as its symbol, which is kind of like a U with an extended edge on the left hand side. So the case is important, particularly with milli and mega. If you get those two confused, you'll be out by a factor of a billion, and that's probably going to cause a problem. There are many more of these, but you know, these are the 6 that I would like you to commit to memory, and you can find a table in the book with the others. So for example, 1 kilogram, I can just replace the meaning of K with its power of 10, which is 1,000. So 1 kilogram is the same as writing 1,000 grams. Similarly with centi here, 1 centimeter, the letter C can be replaced with its meaning, which is 0.01, and so 1 centimeter equals 0.01 meters. I tend not to use the decimal form for these powers of 10. I tend to do what I've done over here and actually write the power of 10 out. So 1 micrometer, we can just replace the mu symbol here with its power of 10. So 1 micrometer equals 10 to the minus 6 meters. So what we can do is we can replace a power of 10 with a letter, or alternatively we can replace the letter with a power of 10 to get the size in terms of the base unit. So that gets us through the basics of the metric system, the 7 different units, and also we introduced the idea of these decimal prefixes that act as multipliers by specific powers of 10. You need to commit to memory 6 of those decimal prefixes, and you need to be able to use them. We'll work through how to use them as we continue. So the metric unit of length is the meter, and a meter is a tiny little bit over a yard, so it's about the length of a baseball bat. Distances in terms of sort of like driving distances are often expressed in kilometers. 1 kilometer is 1,000 meters, or 1,000 baseball bats. In the lab, we're often measuring things on the scale of centimeters or millimeters. They're typical kind of lengths that we'd be looking at for materials that we'd be dealing with in the chemistry lab in General Chemistry 161. Another common unit of length in science is the nanometer, which nano is the decimal prefix, which is equivalent to a power of 10 to the minus 9. And the nanometer is used a lot when we're talking about light. It's visible light has wavelengths of hundreds of nanometers. You'll see that in Chemistry 162, 163. Okay, so that's really kind of the basics of the metric units of length. So the base unit for the metric unit of mass is the kilogram, and 1 kilogram is exactly to, or is about, very close to 2.2 pounds. So that's a kind of, you know, it's about the mass of a quart of milk. So 1 kilogram, kilo means times 10 to the 3. So 1 kilogram is 1,000 grams. In the lab, we're not normally dealing with things in kilograms. We're normally closer to the sort of milligrams to 1 gram kind of scale. So 1 milligram, substituting the power of 10 equivalent to the letter lowercase m, is 10 to the minus 3 grams. So the metric base unit for mass is the kilogram. That's a pretty hefty amount of stuff. It's about the mass of a quart of milk. In the lab, we're normally interested in masses that are sort of 1 gram or perhaps hundreds of milligrams. Okay, so when we're dealing with volume, there's no base unit in the metric system dealing with volume. What we find is that volume will have units of length cubed. So let's first of all consider area. Area is the amount of surface that an object has. And if we look at all of the formulas for these different kinds of two-dimensional objects here, we see that the area always involves squaring some kind of length or multiplying two lengths together. Now, I don't want you to know these formulas. The take-home message here is that the units for area are length squared. It's always going to be one length multiplied by another. So they're going to be things like centimeters squared, millimeters squared, inches squared, feet squared, miles squared, etc. And you're probably kind of used to this concept if you've ever rented an apartment and you're looking at how many square feet it is. They're telling you how much area or floor space is present in that apartment. So volume is a measure of the amount of space that an object occupies, and it's a three-dimensional quantity. And if we look at familiar examples of formulas for the volumes of solids, what we'll see is they always involve three lengths being multiplied together. So what that means for us is that the units for volume are always going to be length cubed. So they're going to be things like centimeters cubed, or inches cubed, or feet cubed, or something that was very large might be miles cubed. And it's important that that you realize that I don't want you to know any of the formulas for area or volume. I'm just using them as examples to show that volume is always three lengths multiplied together, resulting in units of length cubed. So in the SI system, the base unit for length is the meter. So that means that the cubic meter would be the base SI unit of volume. Now that's a lot of stuff, because 1 cubic meter would be a cube that is 1 meters on each edge. And that's way, 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 way more than what we're ever going to be dealing with in the general chemistry lab. Typically, we're going to be dealing with stuff that is kind of like 1 decimeter by 1 decimeter by 1 decimeter, or perhaps 1 centimeter by 1 centimeter by 1 centimeter. So yeah, cubic meter is a lot of stuff. Chemists frequently use non-SI units for volume, and these SI units will often be liters or milliliters. And indeed, in the lab, all of our glassware typically has volume measurements on it that are milliliters, and occasionally we might have some larger glassware that has volume units of liters marked on it. So how big is a liter? A liter is the volume occupied by a cube with an edge length of 10 centimeters or 1 decimeter cube. So a liter would be a cube that is 1 decimeter by 1 decimeter by 1 decimeter. So 1 decimeter times 1 decimeter times 1 decimeter, that would be a liter is the same as 1 decimeter cubed. Now a decimeter is exactly the same as 10 centimeters. So a liter is also the size of a cube that is 10 centimeters by 10 centimeters by 10 centimeters, or 1,000 centimeters cubed. So putting those two together, 1 liter is exactly the same as 1 centimeter cubed, which is 1,000 centimeters cubed, or 1 decimeter cubed. They're all saying the same thing. Now, we have this other quantity here, which is the milliliter, and a milliliter is exactly the same size as 1 centimeter cubed. So we can also say that 1 liter is equal to 1 milliliter, which is equal to 1,000 centimeters cubed, which is also equal to 1 decimeter cubed. In reality, we most commonly measure volume in milliliters cubed, but it's important to in milliliters, that it's important to recognize that 1 milliliter is exactly the same size as 1 centimeter cube. So whether you say milliliters or whether you say centimeters cube, it's really up to you. Okay, so area has units of length squared, so meters squared, feet squared, miles squared, centimeters squared. Volume has units of length cubed, so centimeters cubed, feet cubed, miles cubed, things like that. We also commonly use non-SI units for volume, where we have 1 milliliter is equivalent to 1 centimeter cubed, and 1,000 milliliters is equal to 1 liter, which is also equal to 1 decimeter cubed. So an important concept is that we're going to be trying to develop is this idea of dimensional analysis. And dimensional analysis is just really how we handle units when we're performing mathematical operations. So we've already seen that just like numbers, units can have exponents. So we've had already decimeters cubed, and we've had feet squared, and we've had kilometers cubed. So in mathematical operations, units are manipulated in the same way as powers of 10 by adding or subtracting exponents. So when we multiply 2 powers of 10, we add the exponents. When we divide 2 powers of 10, we subtract the exponents. So 3 minus 2 gives me 1. When we multiply two units together that have exponents, just like for powers of 10, we add the exponents. And when we divide two units that have exponents, just like with powers of 10, we subtract one of the top exponent from the bottom one. And so there's a 1 there that we haven't placed. So we're going to keep that in mind, that we can multiply exponents on units. And what we'll also see is that we can divide and multiply and cancel and do all of the things that we do with the units that we do with regular algebraic symbols. So this is going to be really important as we develop the idea of a conversion factor. So you probably have in mind already what a conversion factor might be. It's something that we can use to convert between one system of units and another. And I'll give you a big hint right now. All of these conversion factors are going to be things that we multiply by, and they will all be fractions. So in chemistry we use this international system. It's of units. It's basically the modern system of the metric system. And something to keep in mind is that this system of units is not really widely used in everyday life in the USA. My understanding is that in the US we are officially a metric country. We're just undergoing the conversion over a really, really long period of time to the metric system. So we're going to have to develop some skill in using conversion factors, and later on we'll see formulas to move between one system of measurements and another. And because of our unique situation in the USA, where people are regularly using both English units and metric units, we're going to have to be perhaps better at doing this than scientists in some other places. Now, there have been a few incidents of unit conversions going horribly wrong, and a good example of this is Air Canada Flight 143. So it's a Canadian aircraft, this guy, and so they have the metric system. This was a relatively new aircraft, and there was a miscommunication between the ground crew and the flight crew, and what happened is this plane got loaded up with fuel, and they loaded up a certain number of pounds of fuel, but they mislabeled how much fuel was on board and labeled it as being kilograms. So we have to keep in mind that there are 2.2 pounds to 1 kilogram. So I don't know how much fuel they would put on board, but just by way of example, 10,000 pounds of fuel does not equal 10,000 kilograms. Right? So these guys mislabeled the pounds of fuel as kilograms, and that's what the flight crew thought that they had on board. In reality, they had half as much fuel as what they believed. So what happened is the pilots, they entered the amount of fuel that the aircraft they had on board into the flight computer. It turned out that they told the aircraft that it had a full tank, when in reality, that it had half as much fuel as what it really did. So these guys were flying along, they hit half a tank, and without warning, everything stopped. The co-pilot had a memory of there being an Air Force base nearby called Gimli, and they were able to glide this aircraft into the Gimli Air Force base. They managed to hand crank down some of the landing gear, but they couldn't get the nose landing gear down, so it kind of came in nose first. And then the other thing that they hadn't realized is that Gimli wasn't an Air Force base anymore. It had been converted to a raceway, and it was Family Raceway, and these are actually Family Race Day, and these are actually like little kids sitting in their cars waiting to start their race when a big aircraft came gliding in out of control behind them. Apparently everybody got off okay, except for the rear of the plane is poking up in the air, and as a result the sliders didn't quite meet the ground, and some guy freaked out, jumped out the back, and ended up breaking an ankle. But my understanding is that they basically flew a tanker in, or drove a tanker in, fueled this guy up, jacked up the nose, got the wheel down, and literally flew it out of Gimli. Another accident that happened was a miscommunication between NASA and a contractor, and the Mars Climate Orbiter. It suddenly became the Mars Climate Keep On Flying, and it failed to go into orbit around Mars, and that spacecraft was lost. So basically, you don't want to be the guy that screws up the unit conversion and, results in, someone getting really seriously hurt, or the loss of, a couple of $100 million worth of spacecraft. So we're going to hopefully learn how to correctly use conversion factors to convert between different systems of units. So you probably have already seen this idea. For two systems of units, we can write, or we can look up, what's known as an equality that relates one unit to the other. And a real simple example of this is we know that 60 minutes is equal to 1 hour. And it's these equalities that we use to construct conversion factors. And so what we can do is we can take the ratio of these two quantities to generate our fractions that are going to be our conversion factors. So 60 minutes divided by 1 hour, 60 minutes is exactly equal to 1 hour. When you put two things on top of one another that are equal, you get the number 1. We could also write 1 hour divided by 60 minutes, and that too would be equal to 1. So you can see what we've done here is we've taken this one equality and we've reorganized it to get two fractions, both equal to 1, and these guys are what we call our conversion factors. Now, if I multiply by one of these fractions, it's the same as multiplying by 1, but what you will see is that it will actually result in changing the units. So how you use a conversion factor is you make sure that your conversion factor divides by the units you want to eliminate and multiplies by the units you want in your answer. So here's a real simple example of a metric to metric conversion. So it says express 1400 millimeters in meters. So the first thing I do is I begin with writing the equality. And I know that 1 millimeter is equal to 10 to the minus 3 meters. All I'm doing there is replacing the meaning of the prefix milli with the corresponding power of 10. So this is the equality that I'm going to reorganize to use as my conversion factor. And in this case, I want to get rid of millimeters and I want to end up with meters. So I need to make certain that my conversion factor has millimeters on the bottom line and meters on the top line. So now I can see that 1400 millimeters, I'm going to multiply this by my conversion factor, and what's going to happen is my millimeters will cancel out, leaving me with my meters. So that's really it. That's how we kind of do this, right? We write the equality between the two units that we want to exchange between. Then we reorganize that to give a fraction where we have the units we want to get rid of on the bottom and the units we want in our answer on the top. So really how I kind of always think about this is write what you've got. So in this case we got millimeters. We're going to multiply by a conversion factor, and we always want the units that we're starting with on the bottom. So I always kind of begin, you know, like that, okay? I'm going to turn millimeters into something else. I know I'm going to use a conversion factor, which is just a fraction, so I put the fraction symbol there. And then the units that appear here, I always make sure go on the bottom of my fraction. And then I kind of think about the rest. So conversion factors can be used to convert between units within the metric system. And when we are doing this, the conversion factors will be based on those prefixes that we discussed earlier. You don't need to know all of them, only the 6 that I mentioned. If you ever need to use anything beyond that 6, you're allowed to look it up in a table. So the conversion factors for conversions within the metric system, doing metric to metric conversions, they're exact numbers. They'll be powers of 10. So here's another one. Express 3.65 kilometers in meters. Begin by finding the equality that relates the two. 1 kilometer is equal to 10 to the 3 meters. All I'm doing is replacing the letter K with its corresponding power of 10. I want to get rid of kilometers and end up with meters. So here I am, 3.65 kilometers multiplied by the conversion factor that has kilometers on the bottom line and meters on the top. So what goes there always goes there. Okay, now kilometers are going to cancel out and I'm left with meters, which is what I want. You can also use conversion factors to convert between different systems of different units within the English system. You do need to be aware that these are not normally powers of 10. I don't expect you to know all of these conversion factors, but they will be exact numbers because they are based on unit definitions. So some of the more familiar ones are 12 inches in a foot, 4 quarts in a gallon, 16 ounces in a pound. Like I said, I don't expect you to know all of them off by heart. Most people don't know, how many cups are in a gallon, or how many, tablespoons or teaspoons are in a gallon, or how many furlongs are in a mile, for example. These can be pretty kind of obscure sort of numbers. So we follow the same principle when we're doing conversions within the English system of units. So it says express 3.42 yards in feet. I need to find the equivalency that relates yards and feet. So I look it up in my book and it says 1 yard equals 3 feet. So I want to get rid of yards and I want to end up with feet. So the conversion factor that I'm going to be using has yards on the bottom and feet on the top. So now we go ahead and use it. 3.42 yards multiplied by 3 feet, just from there, per 1 yard. And again, we'll see that yards will cancel out, leaving us with feet. You always want to do the cancelling and circling of the units that are left, and that should give you exactly what you want. There we go. So we've looked at conversions within the metric system between different units within the metric system, and we looked at conversions between different units within the English system. It's also possible to convert between English and metric and vice versa. Now, it is important to realize, though, that these conversion factors that we're going to use for doing these conversions between metric and English, they're not exact numbers because they're not based on unit definitions, they're based on measurements. And so what that really means is that somebody went out with a centimeter ruler and measured how long an inch is. Someone went out with a centimeter ruler and measured how long a foot is. So these are actually measurements. So we want to use a conversion factor with a large number of significant figures so that it doesn't limit, so the conversion factor is not the thing that limits the quality of our answer. So our conversion factor should always have more digits than our measurement. So here we go again. It says express 3.42 yards in meters. So I have to look up in a table the relationship between yards and meters. And I find this in my textbook. It says 1 yard equals 0.9144 meters. I want to get rid of yards and end with meters. So I need the conversion factor that has yards on the bottom line and meters on the top line. Now I'm ready to go. 3.42 yards multiplied by the conversion factor is 1 yard on the bottom. That's going to leave my yards getting cancelled out, 0.9144 meters on the top, leaving me with meters, which is what I want my answer in. So it's the same process. You are not expected to know any equivalencies other than those based on the 6 decimal prefixes that I mentioned earlier. If you need to do this type of conversion, I will give you the conversion factor, or if it's a homework problem, you'll be looking it up in your book. So we kind of, we've made pretty good progress here. We've defined the metric unit system, and we've learned how to convert between different units within that system. We learned how to use the metric prefixes. We learned a little bit about units of volume and area and how they are length cubed and length squared. And what we've been doing in this final section, on this last section here, which is really, really important, we've learned how to use conversion factors. And so a lot of people will be resistant to using conversion factors and to cancelling units and paying attention to what's happening. And I would say the sooner you get over that resistance and you embrace the use of conversion factors, the better off you will be. Alright, so that's the first part of Chapter 3 that this video is going to cover. I'm going to stop now, and there'll be a second video that covers the remaining part.